Okay, so hello and welcome back. So the next thing that we need to cover here in this chapter is basically in the previous video we went through some definitions of functions, the sine function, the cos function, the tangent function, the cotangent function, the secant and cosecant function. And these are basically all a part of the basic concepts of trigonometry. So we said that about the sine function. We said that basically the sine function is defined as follows: as sine as a function from the set of real numbers to the interval, to the closed interval -1, 1, right? The cosine function, we defined it as the cos function as the set of real numbers to the closed interval -1, 1. The tangent function, we defined it as, so we said that basically all the odd multiples of pi by 2 are going to be taken out of the domain of the function, but otherwise the range of the function is the set of real numbers. So I can write basically tan as a function from r minus basically all x's such that x is equal to 2n plus 1 times pi by 2. These are all the basically odd multiples of pi by 2 and belonging to the set of integers, and this 2 basically to the set of real numbers, right? We also talked about the cotangent function. And we said that the cot function, and basically for this function, because you are the cot function is actually nothing but the cot of x is nothing but cos of x by sine of x, right? So cos of x by sine of x, and so whenever sine of x is equal to 0, then of course the function is not defined, which means that the sine is 0 at 0 and pi. 0 and pi and all the basically multiples of pi. At all the multiples of pi, the sine function is 0, and therefore the cot function would not be defined. And so for the same reason, wherever sine is 0, which is basically all the multiples of pi, cot is not defined. So I have to take basically all points where the pi function, where the sine function is 0, which is all the multiples of pi, out of the domain of the cot function, which means that I need to write r minus basically all x's, such that x is equal to n times pi, where n belongs to the set of integers, and that goes to the set of real numbers. That is for the cot function. Now for the secant function, we said that basically secant of x is nothing but basically 1 over cos x, meaning that wherever basically the cos x is 0, wherever cos x is 0, then of course secant is not defined. So cos is 0 at 0 basically is pi by 2 and 3 pi by 2, right? At pi by 2 and 3 pi by 2, your cos is going to be equal to 0. So that means that all the basically, so you need to go for basically pi by 2, meaning that 1 pi by 2, 2 pi by 2, 3 pi by 2, 4 pi by 2, and so on and so forth. All the multiples of pi by 2. And which means that also you need to go in the other direction as well, which means that for the secant function, basically, if I write 2n plus 1 times pi by 2 and belonging to the set of integers, what happens here is that I have basically, if, for example, let's say that n is equal to 1. If n is equal to 1, then let's say that n is equal to 0, then you have pi by 2. If n is equal to 1, then you have 3 pi by 2. If n is equal to 2, then you have 5 pi by 2. Now over here, basically, okay, right. So what happens is that when you say the odd multiples of pi by 2, then of course, so this is the same thing as 1 pi by 2, right? And then after that, you will not get 2 pi by 2, because 2 pi by 2 would be equal to pi, and you don't want to have this here. So then you have pi by 2, 3 pi by 2, 5 pi by 2, 7 pi by 2, and so on and so forth. Which means that for the secant function, again, what you need to do is, again, do the same thing, meaning that you have to take out all the odd multiples of pi take them out from the domain of the function, because that's where the cos function is 0, right? So I can write the secant function is a function from the set of real numbers minus all x's, such that x is equal to 2n plus 1 times pi by 2, where n belongs to the set of integers, and the codomain of the function is basically the open interval of -1 and 1, because as we saw in the previous videos, the function does not create any values between -1 and 1, and that's how they have defined this function. So I can write r minus the open interval -1 and 1, right? Now for the cosecant function, so what you need to do is that you need to basically take out all of the inputs for which the sine function goes to 0, because you know that the cosecant of x is equal to 1 over sine x. Is equal to 1 over sine x. So sine, where is sine equal to 0? So sine is equal to 0 at 0 and at pi. So that means that if I take care of all of the multiples of pi, meaning that 1 pi, 2 pi, so 1 pi is equal to pi, 2 pi is equal to this angle, 3 pi is equal to this angle, 4 pi is equal to this angle, 5 pi is equal to this angle, 6 pi is equal to this angle, and so on and so forth. So if I take all of those angles out of the domain of this function, then the function, the sine function, cannot be equal to 0, and therefore the cosecant function can be defined. Which means that I'm going to write the cosecant function the cosecant function as a function defined from the set r minus all x's such that x is equal to n times pi and belonging to the set of integers to the set r minus the open interval negative 1 to 1, because the function does not create any outputs between negative 1 and 1, but it is defined at y is equal to negative 1, also defined at y is equal to positive 1, right? So that's basically how we talked about these functions. Now the next thing that we have is that we want to talk a little bit about the inverses of these functions. And that's basically what this whole chapter is all about, the inverse trigonometric function. So now in the first chapter of this book, class 12, we talk about functions and their inverses. And we said that if f is a function from some set x to some set y, such that f of x is equal to y is 1 1 and onto, now then we can define a unique function. Then we can define a unique function, basically called, for example, let's call it g from y to x, such that g of y is equal to x, such that g of y is equal to x, where x belongs to the set x and y is equal to f of x, and y, lowercase y, belongs to the uppercase y. This is the set y, this is the member of the set y. Now here you can say that the domain of g, which is basically this function here, the domain of g, as you can see, is y, which is the range of f. We can say that it's the range of f is equal to range of f. And the range of g which is basically this set x over here, as you can see, is equal to the domain of f. And the range of g is equal to domain of f. Domain of f. Now the function g is called the inverse of f. The function g is called the inverse of f. The inverse of f, and is denoted by f inverse. Further, g is also 1 1 and onto. Well, of course, if f is 1 1 and onto, and if g is the inverse of f, then of course g is going to be 1 1 and onto as well. So you can say that further g is also 1 1 and onto, and inverse of g is f, and the inverse of g The inverse of G is F. Thus G inverse is equal to F. Thus G inverse is equal to the inverse of F inverse is equal to F. We will talk about this expression. So what that means is that, so of course here we said that we had this function F. We had this function F over here, and we said that G is the inverse of F. So if G is the inverse of F, so then I can write F is equal to G inverse, or I can basically, that's the same thing as saying if I say G inverse is equal to F, that implies that G is equal to F inverse. It means that F inverse is equal to G, so these are basically the same expressions. This implies this one, this implies this one. Which means that I can write F is equal to G inverse, or I can write G is equal to F inverse. And of course, suppose that you have some function, for example, F, you take the inverse of that function and you call it, for example, G. If you take the inverse of this function and call it, for example, H, what you will find out is that F is the same thing as H, meaning that you can say that basically, meaning that you will actually end up with the same thing over here, meaning that if you take F and take the inverse of that, and again take the inverse of that function, right, you will end up with F itself. That's all. It is always so. Which means that I can write the inverse of F inverse is equal to F, and of course we know that F is equal to G inverse, or G is equal to F inverse, and so on and so forth, right? So that is basically that. Now now we have a couple more things here to cover, and that is, if you take basically, suppose that you have some function F, and you have also F inverse, which is the inverse of F. Now if you take if you compose F inverse with F, if you compose F inverse with F, what you will get is that, of course, in the discussion about the functions and their inverses, we said that this is going to be equal to I of x, the identity function on the domain of x, which means that I of x is always equal to x. We talked about this in the previous chapter. So therefore I can say that F inverse OF of x is the same thing as F inverse of f of x, which is equal to F inverse of y, which is equal to x, right? Which is basically the same thing. So meaning that basically I of x is basically the kind of function, because it is the identity function on the domain of x, whatever value, the domain of f, whatever value you take from the domain of f and you give it to I of x is going to give you the same thing back. Now all of the values that happen to exist in the domain of f are basically, you have the set x over here, because f is defined as basically x to y, for example, right? And all of the elements belonging to this set are basically x's, right? And since this function is the identity on this set, what that means is that by definition, if I write basically I of x, and if the input is x, the output is always going to be x. which means that, and of course you can see the same thing over here, meaning that if you write f inverse composed with f of x, that's going to be equal to f inverse of f of x. And of course you know that f of x is equal to y by the definitions, by the general definitions that we have. And of course you know that f inverse of y always gives you x, which means that f inverse of x is equal to x. And also what we have is that if you compose, we also said that basically these were two conditions that we use in order to check whether a function is the inverse of another function or not, right? So let's go through them quickly. Okay, so about the functions and their inverses, what we said in the previous chapter of this book, we said that suppose that you have some function f, for example, from some domain f, from some domain x to some codomain y, and suppose that f is basically 1, 1, and onto, right? So it's f is 1, 1, and onto. From this, I can conclude that basically the inverse of f exists, because f is 1, 1, and onto. Now, since the inverse of f exists, I can define some function. G from a set y, from the set y to the set x, such that G is the inverse of f. Now, in order to make sure that G is the inverse of f, we have the following two conditions. Condition number 1, GOF has to be equal to I of x, meaning that the identity function on the domain of the identity function on the domain of f. And number 2, FOG has to be equal to I of y, which is the identity function on the codomain of f, right? Now what these functions do is that this function, the I of x, which is the identity on the domain of f, the input to this function, of course, would be x, because it's the identity function on the domain of on the set x, and the set x basically contains all the x's that we have. The set y contains all the y's that we have. So this function, basically the particular property of this function is that whatever x that you pick from this set x and you give it to this function, it will give you the same thing back. The property of this function, which is the identity function on the domain of f or on the set y, is that whatever y you pick from the set y and give it to this function, it's going to give you the same thing back. And if these two conditions are fulfilled, meaning that if you take the inverse of f and compose it with f, it is supposed to be the identity function on the domain of f. And if you take f and compose it with the inverse of itself, it's supposed to be I of y, which is the identity function on the codomain of f. if these two conditions are met, and this was based on a whole bunch of things that we put together to arrive at these two conditions, meaning that these two conditions, when they are fulfilled, that basically what that means is that many sorts of conditions have been fulfilled, and then as a result these two conditions have been fulfilled, meaning that when you check for these two conditions, you have practically checked for a whole bunch of conditions that have to be fulfilled in order for G to actually be the inverse of F, right? So that's basically what we talked about in the previous chapter, which is kind of actually the heart of the previous chapter. And of course, it's not possible for me to actually explain the whole thing, because then I would have to probably start talking about the whole chapter all over again. But that's basically kind of the gist of the chapter that we discussed before. Now, what we are saying here is that basically F inverse composed with F of X is going to be equal to, of course, be equal to F inverse of F of X. And of course, you know that F of X is equal to Y, so that's F inverse of Y. And you know that F inverse of Y is equal to X, which is, and as a result, you can say that F inverse OF is the same thing as I of X. And also what we have is that F composed with F inverse of Y is equal to F inverse of Y. F inverse of Y is equal to X, so that is F of X, which is equal to Y. And what that means is that F or F inverse is the same function as I of Y, right? Now, if we come back to the sine function, what we will find out is that the domain of the sine function is the set of all real numbers. So the domain of the sine function is the set of the set of all real numbers, which is R, right? Which is R. And the range is the closed interval, and the range of the sine function is the closed interval -1 to 1. Now you can see that of course the function is not 1, 1, because the domain of the function is the whole real numbers, and the range is basically -1 and 1. And then what happens is that you have the function in this manner, and the function keeps going in this way, and then, for example, over here and over here, the outputs are exactly the same, but the inputs are not the same, which means that the function is not 1, 1. And so but basically in this range, if I think of the function in this range, which goes from, for example, -1 to 1 to +1, of course, then over here I can argue that the function is onto. I'm not talking about the whole set of real numbers, I'm just talking about this closed interval, and in this closed interval that the function is onto. And over here we argued that if a function is supposed, if the inverse of the function is supposed to exist, the function has to be 1, 1 and onto. right? Otherwise, the inverse of the function doesn't exist in the first place. So now, to deal with the sine function, first it has to be 1, 1, and then it has to be onto. In order for the function to be onto, of course, we can think about the range of the function. We can basically work with the range of the function, and then if that is the case, then you can argue that the function is onto, and then you have no problems there. So then the function will be onto. And then if you do something such that the function becomes 1, 1, then of course then you can find the inverse of the function. And basically what you can do so that the function becomes 1, 1 is that you have to restrict the domain of the function to some interval, and that interval would be, for example, let me draw the graph of this function properly. So suppose that you have the function f of x is equal to sine x. As you can see, the function starts, for example, if you take from 0 and then keeps going all the way up to pi by 2 pi, 3 pi by 2, 2 pi, and then does the same thing over and over again. Meaning that, for example, between this interval 0 and pi by 0 and pi, or I'm sorry, between 0 and pi by 2, the function is of course 1, 1, because all of the outputs, there is no two equal outputs in the range of the function in this interval. But if I go for example 0 to pi, you can see that you get all of these equal outputs for the function, meaning that, for example, at this point you have this output and this output, and the inputs are actually not the same, they are different. So then you can argue that between 0 to pi, the function is not 1, 1. So now if I want to get this function to be somehow 1, 1, I have to go, for example, from negative pi by 2 to pi by 2. And then again, in this interval, you can see that the outputs of the function, there is no two points where the outputs of the function are equal. And so what that means is that the function would be, for example, 1, 1 from negative pi by 2 to pi by 2, or if you go from 0 to pi by 2, or if you go from pi by 2 to pi, or from pi to 3 pi by 2, or 3 pi by 2 to 2 pi, and so on and so forth. You can go towards the negative direction as well. You can do whatever you want to do. As far as the function, of course, is 1, 1, right? Which means that somehow I need to restrict the domain of this function so that it becomes 1, 1, and then we can find the inverse of this function. So now let's do exactly that. So now if I restrict the domain to negative pi by 2 to pi by 2, then it becomes 1, 1. And the range is negative 1 to 1, which is, and which means that the function is also onto, which means that then in that case the inverse of the function does exist. And you can take any, you can restrict the domain of the function to any of the intervals, for example, negative 3 pi by 2, which is right over here, negative 3 pi by 2, to, for example, to pi by 2, which means that actually that doesn't work. Let me see. Okay, so now there is a slight mistake here in the text that says that actually the sine function restricted to any of the intervals, basically, let me erase this thing over here. It says that the sine function restricted to any of the intervals negative 3 pi by 2 to pi by 2, or negative, for example, pi by 2 to pi by 2, or for example pi by 2 by 2, for example 3 pi by 2. Any of these intervals is 1, 1, and the range is negative 1, 1. Okay. Now, of course, over here, the function would not be 1, 1 for it, because, as you can see, so from negative 3 pi by 2 to pi by 2, so this is negative pi by 2, this is negative pi, this is negative 3 pi by 2, and this is pi by 2, and of course you can see that the function here is not 1, 1. For example, here you can see that the output of the function is 0 for x is equal to negative pi, and here you can see that the output of the function is 0 for x is equal to 0, meaning that the inputs are different, the outputs are the same, which means that the function is not 1, 1. And so that's a mistake. But other than that, if you go for example, negative pi by 2 to pi by 2, you have basically, you can start from here and go all the way up to here, and in this interval, of course, the function is 1, 1. Or if you go for pi by 2 to 3 pi by 2, you would have to start from here and go all the way up to here, and you can see that over here the function is actually 1, 1. So, and then of course you can just keep going with these intervals. From basically, you can go towards the negative infinity, you can go towards infinity, and wherever you go, of course, the range is going to be negative 1 to 1, right? So we can therefore define the inverse of the sine function in each of these intervals, and we denote the inverse of the sine function by sine inverse or arc sine function. So the inverse of the sine function, is denoted by basically sine inverse function, and which is called basically the arc sine function. Some calculators call it the arc sine function. And so then you can say that the sine inverse function is a function whose domain is negative 1 to 1. So then you can say that basically, let me go up here because I don't have enough space. 248. Thus you can say that, so because we said that basically the sine function is a function, we said that the sine function is a function whose domain is basically the set of real numbers, and the range is basically but actually what's important here to understand is also one more fact, and that is when you write your functions in this notation, well, what this means is that basically this notation is actually referring to the for example, if I write over here -1 to 1, this actually is referring to the codomain of the function, right? But here basically we said that we defined that the sine function as basically the set of real numbers to the closed interval -1 to 1, because most probably they wanted the function to be invertible, right? That's the explanation that I have for this. Otherwise, I don't really know why they have done this, because you can simply say that the sine function, you can define it as the set of real numbers to the set of real numbers, right? So this becomes the codomain of the function. This becomes the codomain, this becomes the domain. And then you can argue that the range of the function is equal to the closed interval -1 to 1, and we would have no contradiction, no problem here. There are thousands of functions. I mean, you are actually logically allowed to basically to define a function such that, for example, you can say that, for example, a function f goes from R to R, for example, all the real numbers to all the real numbers. But then the range of the function is a subset of the set of the real numbers, and that would be, for example, this case over here. But for whatever reason, which we will hopefully find out shortly, they have defined the function as basically the set of real numbers to the closed interval -1 to 1, and that way, of course, then you don't have to really have to be worried about the codomain and the range of the function. In this case, the codomain and the range would be the same, and so the function would be invertible, provided that you take care of the domain of the function, of course, right? So based on the discussion that we had, we can define the inverse of the sine function in each of those intervals. For example, you can go from -π/2 to π/2, right? So you can take the domain as this interval, or you can take it as π/2 to 3π/2, or you can basically pick any interval that you want, right? This would be the domain of the function if you want the function to be invertible. The range of the function or the codomain of the function is okay, there is no problem with that. And with that in mind, then you could say that basically, and we said that basically the inverse of the sine function, the inverse of the sine function is the sine inverse function, which we call also as the arcsine function. Arcsine function, right? Now the arcsine function is basically, so then based on this whole discussion, you can say that thus basically sine inverse function, sine inverse is a function whose domain is basically the set that we have over here. We have to take this as the domain, is the closed interval -1 to 1, and -1 to 1, and the range could be any of the intervals, and the range could be any of the intervals for example, -π/2 to π/2, or you can go for example, pi by 2 to 3 pi by 2, 3 pi by 2, and so on and so forth, right? So now what happens is that, for example, if I take the function, for example, if I take this function here as, for example, from negative pi by 2 to pi by 2, you can see that I get this part of the function, meaning that the function goes from here all the way up to here, right? Let me see if I can. No, I don't really know how to do that. So I get this part of the function. Now that is basically f of x is equal to sine x. Now the inverse of this function, I can say that right now you can see that the range of this function goes from negative 1 to 1. So that range, I can take it as the domain of the domain of the sine inverse function, and then basically meaning that what I need to do is that I need to take the sine function, basically the sine function we defined it as basically the set of real numbers to negative 1 to 1. So therefore I have to basically calculate or define the sine inverse function as a function from negative 1 to 1, and that has to, of course, that cannot go back to R, because if I send it back to R, then I will have the problem that the function is not 1, 1. So I have to pick some interval over here over which the function is 1, 1. So for example, I choose negative pi by 2 to pi by 2, right? Which means that basically, which gives me some function like this, meaning that I would have f of x is equal to, let me take some functions here, the sine inverse of x. And as you can see, the sine inverse function is actually, they have taken care of this problem, meaning that the domain of the function goes from negative 1 to 1, as you can see, negative 1 on the x-axis all the way up to 1 on the x-axis, and the range of the function goes from this point, which you can see as negative pi by 2 to pi by 2. You can see that this is pi by 2, and that's exactly what we did over here. So of course it's possible to do whatever that you want. It's of course possible to do whatever it is that you want to do, meaning that you can take the range of the function as pi by 2 to 3 pi by 2. In that case, the function would be 1, 1 as well. You can take it as negative pi by 2 to pi by 2. You can take it as, for example, I don't know, you can take it as for example, 3 pi by 2 to 5 pi by 2. You can pick this one as well, or you can go from 5 pi by 2 all the way up to 7 pi by 2. You can even go from 5 pi by 2 to 3 pi. All of those things you can of course do. But because there has to be some sort of agreement in mathematics, and of course whichever sort of interval you want to take over here, you will, as you can see here, you will get a branch of the sine inverse function. As you can see, we got a branch over here for the interval, basically negative pi by 2 to pi by 2, for example. And then relative to any other basically domain that you choose in the sine function, you would get some other branch over here, right? Meaning that the function would be transferred up and down the y-axis, of course, but between the same x's, negative 1 and 1. So now what they have done, in order to have some sort of agreement, they have defined the inverse, the sine inverse function as follows. So they have basically, what they have done is that the branch with range negative pi by 2 to pi by 2, with range negative pi by 2 to pi by 2, right, is called the principal value branch, is called the principal value branch, whereas other involves as range, whereas other involves as range, give different branches of the sine inverse function. Give other branches of the sine inverse function, right? So what that means is that, what I'm going to do is that I'm going to define the sine function as, basically, normally the sine function is a function that goes from the set R to negative 1 to 1, right? And of course, the function is not 1, 1. The function is not 1, 1, and of course, therefore the inverse does not exist. Now, in order for the function in order for the inverse of the function to exist, I'm going to define sine as the function goes from the interval negative pi by 2 to pi by 2, and the range of the function I'm going to define as negative 1 to 1. And now the function is 1, 1, and it is of course onto as well, and therefore the function is 1, 1 and also onto. Since the function is 1, 1 and onto, therefore the inverse of the function, exists. Since the inverse of the function exists, therefore I can define the inverse of sine as sine inverse, which is the arc sine function, as basically negative 1 to 1 back to negative pi by 2 to pi by 2, right? And this function, and there is something important to note here, meaning that, for example, just as I defined the sine function from negative pi by 2 to pi by 2 to negative 1 to 1, I could have defined the function as, for example, something like negative pi by 2 to 3 pi by 2, right? I could have written, for example, the sine function, I could have written it as a function from, for example, pi by 2 to 3 pi by 2, and still the range of the function would be negative 1 comma 1, and then the inverse of the function would be, and here basically the function again is 1, 1 and onto, the inverse does exist, and so then I can define the inverse of the sine function as the function from negative 1 comma 1 2 pi by 2 comma 3 pi by 2. That would give me another branch of the sine inverse function. And you can see where this is going, meaning that I can just keep choosing different intervals here, and I would get an infinite number of definitions for the sine function and for the sine inverse function. And therefore, this way, there would be no agreement between people, meaning that if I said, for example, the sine inverse function, nobody would understand what I meant by the sine. Nobody would understand what is the domain of the function, what is the range of the function, what is the codomain, and so on and so forth. And so, since having an agreement is essential and important in mathematics, what we have done is that we have defined basically we have defined the sine function just for the sake of the inverse as having the domain negative pi by 2 to pi by 2 and the range as negative 1 to 1. And therefore the inverse of the function has become the sine inverse function going from negative 1 to 1 to negative pi by 2 to pi by 2. And that has been called the principal value branch of the sine inverse function. The principal value branch of the sine inverse function. Of course, you do understand that basically, other than that, you can define, of course, anything as long as the inverse exists. You can, of course, define the inverse and you can work with it. But this one is called the principal value branch of the sine inverse function, right? So, and of course, then basically you can argue that other intervals as range will give different branches of the sine inverse function, right? And so the next thing that we have is, so when we refer to the function sine inverse, when we refer to the function sine inverse, we take it as the function, as the function whose domain is negative 1 comma 1, the closed interval, and the range is negative pi by 2 to pi by 2, right? And we write the sine inverse function is basically a function from the closed interval negative 1 to 1 to negative pi by 2 to pi by 2, right? From the definition of the inverse function, so from the definition of the inverse function, it follows that basically the sine inverse of x is equal to x if, of course, you have to take care of your domain and the codomain and everything here, meaning that the argument of this function would be, of course, x, and x has to be defined here, meaning that x has to be a member of this interval, meaning that provided that x is basically -1 is less than or equal to x less than or equal to 1, right? And this is because, I mean, what this happens is that we said that the f inverse of y is equal to y, and we said that f inverse of f of x is equal to x, right? And you can write the same things as f composed with f inverse of y is equal to y, and you can say that, of course, f inverse composed with f of x is equal to x. And so here basically you have the sine function, you have you're calculating the sine of the sine inverse function, which is the same thing over here. The sine of sine inverse x is equal to x, basically whatever your input is, of course, provided that basically your x is defined here, and x can be defined if basically x based on this definition is some x between -1 and 1, including -1 and 1. And you can say that basically, by the same logic, you can say that basically the sine inverse of the sine x is equal to x if, so basically we said that we restricted the domain of this function to -π/2 to π/2 so that the function was invertible. So then x has to be between -π/2 and π/2, I suppose. So if -π/2 is less than or equal to x, less than or equal to π/2, right? Now, in other words, you can say that if y is equal to sine inverse x, if y is equal to sine inverse of x, then sine of y is equal to x. Then sine y is equal to x. And the reason for that is that suppose that y is equal to sine inverse x, y is equal to sine inverse x, then sine of y is equal to x. Basically you need to be a little bit creative with these variables. They choose these variables not always in the right order, meaning that whenever we talk about functions, we always have some x and some y over here, and we say that, for example, there is a function f that takes you from x to y, and there is some other function, for example f inverse, that takes you from y to x, right? So this is how f and f inverse work. Now we always assume that, for example, this set x contains all of the x's that we have, and we always assume that this set y contains all of the y's that we have. So we can say that then, for example, f of x is equal to y, right? And that makes sense in this situation. Or then you can say that, for example, in the same situation, f inverse of y is equal to x, right? Now what they have done here is that they have basically kind of mixed everything up, and you need to understand what they mean by these statements. Meaning that what they're saying is that you are you have basically some set x over here and some set y over here, and you have some function over here, let's call it sine inverse, right? So if I have some x over here and some y over here, and if the sine inverse of x is equal to y, then of course sine of y is going to be equal to x. So it does actually make sense. But then it's kind of meaning that normally what you would imagine is that, for example, you have the sine function up here and then the sine inverse function down here, meaning that the sine inverse, we take it as the inverse of the sine function, and usually not the other way around. But of course, logically, you can say that the sine function is the inverse of the sine inverse function, and everything works out okay. Logically, there is no problem with it. Moreover, we have a couple of remarks here, and we will discuss them in the next video. I'll see you in the next video, and thank you.